Okay.
And for the last three talks, we start with Arkady, Tseytlin, who is going to tell us interesting thing about correlators of Wilson loops when we go across things and AdS2 CFT1.
Okay, thank you much. So I will review some recent work with Mathieu Beccaria and Simone Giambi, and also Rada Roybon earlier, which is related to this, to the title. So it will be related to very closely to string worldsheet, but also to AdS N equal 4 Super-Yang-Mills AdS5 S5 string. So the main part of my talk will be about Wilson loops with correlators, with operators inserted along the Wilson loop. And I will be considering both supersymmetric Wilson loop and standard Wilson loop. So supersymmetric is Wilson-Maldacena loop, where we have extra coupling to scalars, and standard Wilson loop is just the usual original integral of exponent of integral of A. And these considering operators inserted on the Wilson loop leads to kind of interesting examples of what may be called defect CFT, a kind of a one-dimensional CFT which is induced from four-dimensional CFT of N equal 4 Super-Yang-Mills. And from AdS side, that leads to kind of example of AdS2 CFT1 duality, where AdS2 theory is essentially defined by string action itself. So we'll be considering worldsheet theory and computing Witten diagrams in AdS2, which is actually the metric on the worldsheet. So I'll explain how this comes about later, but I will start with some general remarks about Wilson loops. In fact, comparing standard Wilson loop, which is an important observable in any gauge theory, to Wilson-Maldacena loop, which one can think of it as kind of imported from 10-dimensional Wilson loop, where in addition to usual coupling to gauge field, we have coupling to scalars of N equal 4 theory. And if we choose the kind of the contour in these extra 6 directions in a special way, so that the square of x is square of x dot is the same as square of y dot, then this Wilson loop becomes locally supersymmetric and has better properties. In particular, choosing, say, straight line Wilson loop or circular Wilson loop, one gets half of BPS, half of supersymmetry preserved, so it's a BPS object. And for example, for straight line, one just gets no divergences and expectation value is 1, and for circular Wilson loop, the expectation value can be computed exactly. So there are certain important features in this case which allow us to use, say, localization to compute certain Wilson loops, and so supersymmetry is quite important. But one may ask what we can say about ordinary Wilson loop in the context of N equal 4 theory, and this is not a BPS object, and say for straight line or circle, but it's still quite likely that standard Wilson loop expectation value can be still computed using possibly integrability. This has not really been done so far, but that's one of the motivations to look also on Wilson loop. And in fact, the two cases, Wilson-Maldacena loop and Wilson loop, they are kind of two special limits in the sense of if one looks at randomization of Wilson loops. So as I'll try to review now. So from AdS5, from the string side, Wilson-Maldacena loop corresponds to choosing a particular point in S5. So we impose Dirichlet boundary conditions on the scalars in S5, and that preserves supersymmetry. In the Wilson loop case, one imposes Neumann boundary conditions in S5. So that means the zero mode on S5 will be, we need to integrate over it essentially. And these boundary conditions happen to be non-supersymmetric, and that's why the standard Wilson loop is non-supersymmetric. So, as I mentioned, the main part of what I'm going to talk about will be about correlation functions, but so this correlation function will be of operators inserted in a line, and in the case of supersymmetric Wilson loop, that will be a one-dimensional theory which has essentially an equal-8 one-dimensional superconformal symmetry. And for Wilson loop, there will be no supersymmetry, so there will be just global SO3, SO6 symmetry, in addition to conformal one-dimensional SO1, 3. Again, I'll get back to that in more detail, but the point is that these two cases define different CFT1 on the line. So it's useful to think of a more general class of Wilson loops, which was introduced by Palczynski and Sully, where we put some parameter zeta in front of the scalar coupling. So here, phi m, again, scalars of Super-Yang-Mills, 6 scalars. Theta m is just a constant vector, so we can choose it, say, in 6 directions. So this is just phi 6. This is modulus over the x dot of the contour. So looking at this Wilson loop operator, this generalized Wilson loop operator, where zeta equals 0 is Wilson loop and zeta 1 is Wilson-Moldacena loop, we can see that we need to randomize this zeta parameter. So it will be running with randomization scale. So this, in contrast to ordinary Wilson loop or Wilson-Moldacena loop, where there are no divergences, no logarithmic divergences in the expectation value of them, here one will need also to randomize this zeta. So what happens is that essentially this zeta runs with scale, and there is a one loop beta function looks like this. So lambda is Toft coupling. So I always discuss Lagen theory. So lambda is Toft coupling. We consider weak coupling, lambda much less than 1. And the beta function for this zeta has this structure. So zeta squared minus 1. So there are two zeros, zeta 0 and zeta 1. And these are precisely the Wilson loop and Wilson-Moldacena loop. So they are UV and infrared conformal points of this one-dimensional RG flow. So one can view this as one can view, say, zeta equals 0 point, which is Wilson loop, and perturbed near it by phi 6 operator, which is this, that's what I call phi 6. And then one can, doing perturbation theory, one can reach this zeta equal 1 point. So that's the flow connects these 2 points. So that picture is kind of useful because one can think of also expectation value of Wilson loop is effectively some partition function of, or log of free energy of some one-dimensional conformal field theory in which this zeta is a parameter. Now,
are you saying that there are no other renormalizations?
No, there are no. Yes, so for ordinary Wilson loop or for Wilson-Moldacena loop, there are no. So I will be assuming mostly. Here the contour is not important, as long as there are no cusps, etc. I'm considering a smooth contour. So for smooth contour, there's nothing else. So for Wilson loop, there may be power divergence, linear divergence, etc. We can regularize them away, but the point is there are no logarithmic divergences. So in these two fixed points, there are no logarithmic divergences. Now, so for Wilson-Moldacena loop, there is an exact result for expectation value for a circular Wilson loop, which is just given by Bessel function. It's a famous result, which was confirmed by localization. Now, this formula at weak coupling looks like 1 plus corrections in lambda, and at strong coupling, it has characteristic exponential behavior plus prefactors and then corrections. So for straight line, again, this symbol 1 means zeta equal 1, so this is Wilson-Moldacena loop. So for straight line, the Wilson-Moldacena line expectation value is just 1, and the reason why this is 1 and this is non-trivial was suggested explanation was this kind of conformal anomaly, because straight line is related to circle, and we could expect that conformal symmetry is preserved here. So why we get the difference? Because one possible explanation is that it has to do with infrared behavior vector propagator, at least in perturbation theory, and that was a suggestion by Gross and Drucker. So I think it was not in your paper, but in their paper, yeah. Yes. So then one could say, well, Wilson loop couples just to the vector, so maybe presumably the same picture applies to Wilson loop as well. And the answer is no. In fact, Wilson loop and Wilson-Madsen loop happen to have the same leading terms at small lambda and at large lambda, but subleading terms are different. So expectation values of Wilson-Madsen loop and Wilson loop are actually depending on zeta. So at weak coupling, for any zeta, the leading term is the same. So one loop term doesn't depend on zeta, on this parameter. And a very strong coupling also, there is no dependence on this parameter, because both Wilson loop and Wilson-Madsen loop are still given by minimal surface in AdS5, which just ends on a line at the boundary or a circle at the boundary, and that's described by AdS2 geometry. And for the circular boundary, the area, the randomized area is just the same. But subleading terms will be different. And that's actually significant from the point of view of interpretation of expectation value of Wilson loop as some kind of partition function in one dimension. So in perturbation theory, we just computed what is the subleading two-loop term in the expectation value. It happens to have this form. So if z equals 1, that's Wilson-Madsen, that reproduces this 192 in this Bessel function expansion. But for z equals 0, it gives a different coefficient, and it has different transcendentality compared to the supersymmetric Wilson line case. So the interesting question, what can one actually compute this expectation value to all orders? Maybe using integrability, because this for Z1 we have localization, etc., but here we don't have other means. But that seems an interesting question, what's the exact expression. Now, if zeta is not equal 0 or 1, at 3 loop orders there will be logarithmic divergence, so we'll need to randomize this zeta parameter according to that beta function which I have shown earlier. So the randomization here starts at 3 loop order. Now, taking derivative of this expression over zeta, we get it's easy to see, we get precisely up to coefficient, we get precisely this beta function. So that's expected relation between kind of familiar relation where you have derivative of free energy over coupling proportional to the beta functions. Now, in odd dimension, and d equal 1 here is we're dealing with d equal 1, so in odd dimension there is a suggested F theorem, analog of C theorem in even dimensions. And this F theorem states that essentially infrared free energy, so here it's F tilde is minus free energy. So infrared free energy is bigger than UV free energy. So for log partition function, just the opposite. And that same relation we observe here. So it's kind of remarkable that indeed this expectation value of Wilson loop, it does have interpretation of some kind of partition function, which is not surprising from string side, because on string theory we have Wilson loop defined as expectation value on a disk. So it's kind of natural interpretation. So this, so Wilson loop for Wilson loop is expectation value is bigger than Wilson loop, Wilson-Madsen loop. In perturbation theory, just that follows from this formula. So as zeta is 1, that's a minimum, and zeta equal 0 is bigger than zeta equal 1. So
the statement that only renormalization comes to zeta, is that the old loop statement?
Yes, that's an old loop statement for ordinary Wilson loop in just Young-Mills in any gauge theory. The statement is that the only if you ignore power divergence, the only randomization is due to coupling. In n equal 4 theory, coupling is not running. So in that sense, they both are conformal objects.
So what happens for zeta equal to -1? It seems that
It's a symmetry. You can if you set scalar to minus scalar, it changes. So it doesn't matter. Yeah. So another point is that given this beta function, one can actually, as I mentioned, this flow can be thought of as driven by phi 6 operator inserted in this exponent. Taking derivative of beta function over this coupling zeta near point zeta equals 0, zeta equal 1, these two conformal points. One can learn what's the dimension of this operator phi 6 near these 2 points. Again, dimension of phi 6 in the sense of operator inserted on a line. Yeah, so to be clear, what I'm trying to say is that this is our phi 6 operator. So if you put it down, if we expand in powers, that will be inserted in this trace path ordering. So in that sense, viewed as a one-dimensional operator, operator on the line, it has dimensions near Wilson, near this Wilson-Maldassana loops, near the supersymmetric point, it has dimension 1 plus lambda over 5 pi squared, and near Wilson loop dimension, it has 1 minus. So this will be significant because we'll see what's the dimension of this phi 6 should be a strong coupling, and there will be a suggestion of smooth interpolation between weak and strong. So a strong coupling interpretation of Wilson loops in AdS5S5 is that they are given by string path integral or with given boundary conditions for the contour on the boundary of AdS5. So for this straight line or circle, it's essentially AdS2 minimal surface classically, and then we can compute corrections to it. So for Wilson-Maldassana loop, the result which follows from this Bessel function formula is like this, and indeed we can interpret the square root of exponent square root of lambda as a minimal area, and this prefactor was suggested has some interpretation of possibly Möbius normalization of Möbius volume on the disk. So that's one possibility. But in the case of Wilson loop, this prefactor changes, and it's a very simple reason for that. It's 5 extra zero modes on S5. So because we have Neumann boundary conditions now for the scalars on S5, we don't fix particular point in S5 due to this, which was in the case of supersymmetric Wilson loop, where we have coupling to phi 6 in the exponent. So here, we have Neumann boundary condition which kill this zero mode. So here we have zero mode, and these 5 zero modes essentially change. Square root of lambda is like alpha prime, 1 over alpha prime. So that changes normalization of a prefactor. But the consequence of that is again this relation which is consistent with F theorem. So this expectation value of so log of partition function in kind of UV is bigger than this log of in the other fixed point. Now, the main part of what I'm going to talk about is indeed the map of how we interpret operators on the Wilson line in terms of fields, string fields. Now, in the case of Wilson loop, the full 06 symmetry is unbroken. We don't have coupling to the scalars in the Wilson loop. So when we insert operators along the line, the 06 symmetry is unbroken. And in fact, as we'll see, the scalars, Young-Mills scalars should be identified essentially with embedding coordinates of S5. So whichever 6, and so correlations of these embedding coordinates with will be mapped into correlators of phi. In the case of supersymmetric Wilson loop, 06 is broken to 05 because of this phi 6 appearing in the exponent, and here the scalars, the 5 remaining scalars, they will be related to 5 scalars of Young-Mills, those not coupled to Wilson loop. And phi 6 will be kind of composite operator. It will be square of these string coordinates. Now, interesting point which was suggested by Palczynski and Sully, one can think of the interpolation between these Dirichlet and Neumann boundary conditions on string side also as a kind of RG flow, where we perturb string action by a term where we add a boundary term, which is just like some kind of boundary tachyon of potential of coordinates. And we just choose it to be y6. So in this case, y6 is just 1 minus square of y squared, this S5 coordinates in near particular point. And it's easy to see, just taking variation of YA, that leads to Rabin boundary conditions in general. So, yeah, I think it died. This died. So this couple is some other coupling which is not really important, but it's very easy to see that we know that if we add some function of string coordinates to if we add some boundary perturbation like tachyon, open string tachyon thing, the beta function for that coupling will be essentially Laplacian, in this case on S5. And if you add something which is linear in embedding coordinates, in case of S5, that has eigenvalue precisely 5. So it's just linear in Y. So it's like, in general, it will be J plus 4, the usual Casimir. But in this case, it's just 5. And one can easily see that the beta function should be minus 1 canonical dimension plus 5 over square root of lambda, which is tension. Anyway, the reason why I'm mentioning this, and we'll actually get to this 5 square root of lambda later in a different way, that allows us to think of what are the dimensions that taking derivative of this beta function over kappa, what are dimensions of the corresponding perturbation, or this y6, or this composite operator, near the two fixed points, 0 and 1. And in this case, near Wilson loop, near non-supersymmetric case, or near Neumann boundary condition, that will be 5 over square root of lambda, and the other one is 2 minus 5 over square root of lambda. And these expressions, so a strong coupling basically means that dimension should be 0, but at weak coupling it goes as 1 minus, so that suggests kind of smooth interpolation. If you increase the coupling, you go lower, below 1 to 0, and here the opposite, you go from 1 up to 2. So that's actually all I want to say at the moment about this story. So let's now switch on to details about correlation functions on the Wilson law. So in some sense, it's a kind of novel sector of observables in AdS CFT, where we look at Wilson, not just expectation value of Wilson loop, but also at correlators along Wilson loop. Yeah.
So are you assuming that there is some kind of a decoupled sector with degrees of freedom localized on the Wilson boundary?
Yes. So from Young-Mills. No. In which sense decoupled? Yeah. So that may be a good question. So from Young-Mills' point of view, actually I'm getting to. I think I'm getting to this. So from Young-Mills' point of view, you just look at trace path ordered exponent and you put fields, elementary fields, f, scalar derivatives along the line.
But these are part of sort of four-dimensional, part of four-dimensional.
Yes, these are part of four-dimensional conformal theory, but you can think of them as defining their correlators, defining some effective correlators of one-dimensional conformity theory, and they will satisfy all the right properties of one-dimensional conformity theory. So in that sense, it's perfectly self-consistent theory as kind of induced one-dimensional conformity theory. There's no intrinsic, what is not known how to define it in intrinsic terms, say by some one-dimensional action. And that's one of the interesting open questions. Okay, so the main point will be, so I'll first discuss mostly BPS case, Wilson-Maldacena loop. So in this case, empty Wilson loop defines a kind of supersymmetric vacuum, and then we insert along it elementary fields. So these will be scalars, components of field strength orthogonal to the line, and that will be kind of displacement operator. And they will be dual to string coordinates on AdS2. I will try to motivate why. And that can be compared to our usual closed string vertex operators being dual to traces of products of fields at one point, correspondence. So that's what we usually compare in the case of closed strings. So this is more like coming from an extra open string sector where you have open strings in AdS5 ending on the line, and then you consider also localized perturbations along the line. So what we'll be doing is essentially computing Witten diagrams similarly to what is done in this case, in the case of AdS5 S5, but here it will be all restricted to AdS2 S2. To AdS2, sorry, without S2. So in more detail, so if we take straight line, so just I'll parameterize it by x0 equal t. So that's our Wilson loop, Wilson-Maldacen loop with phi 6 coupled. And we have straight line, so there's no prefactor here. X dot is just 1 in the 5, 6 term. So these double brackets just mean we're essentially these correlators. So we consider trace path ordered exponent with exponents between the operators, local operators, say components of field strength or scalar. And we want to compute this correlator as a function of T1, Tn. So essentially, one motivation for looking at these objects is that they can be thought of also equivalent to some kind of deformation of Wilson loop. Instead of considering straight line, you consider some wiggled line, and then you can mimic these wiggles by insertion of these operators. And in fact, a complete knowledge of these operators will help us to define any deformation of circle of straight line or circle. So symmetry is preserved by this by straight line they are SO5 because that's what remains of SO6. So there are 5 scalars inserted on the line that will be invariant on the SO5. Then there is SO2, 1 part of conformal group, and also SO3 just rotations of the line, along the line. So we'll put line along x0, so the xi rotation. So SO2, 3 is just one-dimensional conformal group, including dilatations, translations, and special conformal transformation along the line, plus 16 supercharges. So that whole thing is n equal 8 in one dimension, in t equal 1, n equal 8 superconformal group. So the operators in certain line they'll be classified by representation of this group, and then we just compute their correlation function of these for example, elementary or short representation. And the claim is that at weak coupling one can more or less argue that systematically that these correlators will be satisfying all required properties of one-dimensional CFT. So we don't really need to make any reference to n equal 4 theory. They will formally define some CFT1. Of course, it's important that original theory is conformal, but once we compute... Yes, yeah. Well, there's no intrinsic... Well, that's an open question. So we just get correction, we get dimensions, we get correlation functions, which will be factorized, etc. They will satisfy usual conformal word identity. But what I don't know from which one-dimensional theory it comes from, if you're asking that question.
When you say satisfy conformality, are you assuming, are you considering particular shape of Wilson line?
Straight line. So I'm just discussing straight line with insertions. Yes, of course. In the case of Wilson loop, it will be a different conformal theory. If I consider not Wilson-Maldacen loop, but Wilson loop, without coupling to scalar. So that's also what I'm going to discuss. So the main interest is this elementary excitation. So short representation of this group, it's 8 bosonic plus 8 fermionic operators with protected dimensions. So these are essentially these scalars, 5 scalars that do not couple to the loop, and 3 displacement operators. These are components of field strength. T, again, T is along the line, it's Euclidean time, and covariant derivatives of phi 6. They happen to have this interpretation of displacement operators, and they have protected dimension delta, obviously equal to. And why they're protected follows from some word identity related to orthogonal translations to the line. So the correlation functions of these 5 scalars and these displacement operators, their dimensions are protected, so they have this form. So these functions CF, C phi and CF, they actually happen to be related to what is called Bremsstrahlung function, which is essentially, it appears also in the discussion of Katz's anomalous dimension, but it can be also computed exactly in terms of Bessel function, so it's not unrelated to the circular expectation value. So anyway, so they are known exactly, but the interesting question would be higher point correlation functions. And since there's no anomalous dimensions, these functions actually are scheme independent, so they have precise meaning. So then there will be 3-point functions which actually vanish by this symmetry, but the question will be to compute 4-point functions. And not much is known at weak coupling, and we will be discussing them at strong coupling. That would be the main topic. So they will depend, obviously, on 4-point function will depend on one-dimensional cross ratio, combination of these T1, T4, and coupling. So on string side, so we start from AdS5 S5 string, and we consider minimal surface ending on the line on the boundary, and the minimal, the geometry on this minimal surface is AdS2, and then we look at fluctuations near this minimal surface. So essentially what the picture is that you have fundamental open string which ends on the boundary, stretched in AdS along the Z direction, and minimal surface is kind of the yeah, I have a picture somewhere. Oh. Yeah, it's something like that. So that's AdS2 inserted in AdS5, and these are the correlation function which we may want to compute. So the main important piece of information is what are the fluctuations near this AdS2 minimal surface. So we just start with AdS5 S5 string and fluctuate and expand the action near this minimal surface. We get 5 massless scalars in S5, 3 massive scalars in AdS5. These are orthogonal fluctuations to this minimal surface, which I have just shown, and they have mass 2. And so these are xi, and there are 8 fermions with mass 1. And these 8 plus 8 fields are precisely on symmetry grounds. They match these elementary fields of 5 scalars and Young-Mills and 3 displacement operators and the corresponding fermions. And this identification is also natural if you want to think of, again, considering some wave fluctuations away from straight line. On Young-Mills, they'll be mimicked by insertion of elementary fields along the line. And on string side, changing the minimal area means we change the coordinates, string coordinates. So this identification kind of seems well motivated. Now, in general, in AdS, we have this standard formula between dimensions of the dual operators and masses. So if we have a massless scalar with usual Dirichlet boundary conditions, that corresponds to d equal 1 here in AdS2, so that will be delta equal 1 dimension for m equals 0. For m equal 2, it will be dimension 2. So that's precisely the right dimensions for scalars and displacement operators in Young-Mills. So again, I already mentioned, so what is going on here is really where kind of we can pretend we can see elementary gauge fields as long as they are inserted along Wilson line. And this is a gauge invariant object together with Wilson line. And they, on string side, that's why we can actually identify them with something which is meaningful also at strong coupling, which are string coordinates themselves, fluctuations away from minimal surface. So one can, of course, we'll be looking only at this correlation function of these elementary string fields, but one can also look at various other sectors. For example, one can insert closed string state together with Wilson loop and compute the expectation value. So that'll be like putting a point away from the line. And also various other, some of them were discussed, but one can also look at closed strings inserted, not only, say, scale at point inserted, but square of scale inserted on a point, etc. So that will be various other sectors. So the strategy will be just to start with string action itself and expand near minimal surface, and then string action will provide the vertices which we'll be using in tree-level Witten diagrams in AdS2. And that will lead to prediction for 4-point functions of these protected operators inserted on the Wilson line. So in a sense, it's good to have a kind of draw analogy with what we do usually for closed strings in AdS5. Say we start at strong coupling from supergravity action, which has n squared in front of the Einstein term, and we basically compute say 4-point function just in supergravity approximation, and we'll get 1 over n squared correction. So here we start instead with string action, which roughly has this form where square root of lambda is a string tension. So here corrections will be in 1 over square root of lambda. So here, instead of target space graviton, our elementary fields are actually string coordinates. So string action is ultraviolet finite and as viewed as two-dimensional CFT and QFT in AdS2. So in fact, this AdS2 CFT1 duality should hold to any order in square root of lambda. So because just like string theory in target spaces, ultraviolet finite, it's well defined. So the same should be true here. There will be should be no extra ambiguities or extra parameters which we need to tune. So then one can compute Witten diagrams. In principle, one should be able to compute tree level and loop corrections, and few loop corrections were computed, but in fact that needs to be done more systematically, and as Al mentioned earlier. So for example, what was done in this case earlier was 2-point function, and this coefficient C5, which was, I think I mentioned, at strong coupling, one can compute this C phi, which should be related to the Bremsstrahlung function from supersymmetry, and indeed one could check that subleading term from string side does agree. So 4-point function, so that will be what I'm going to discuss now. So computing 4-point functions and then using OPE just at leading order in 4-point functions at first at leading order in string tension, and then oh, yeah, I was very slow. Okay. So, no, well, actually, I said more or less what is relevant. So, yes. So that's a string action. So that's a minimal surface. So induced geometry is AdS2. So now comes the key point. So we can parameterize AdS2 in such a way that we isolate AdS2 part. So x are 3 coordinates which are orthogonal to AdS2. So we choose static gauge in the string action. So it's a usual Nambu action. If you choose static gauge instead of this AdS2, you get this AdS2 metric. And then this is the total induced metric. So this is S5 part, this is AdS2 part. And expanding near in fluctuations xi and ya, we get Lagrangian, which is or action, which will involve these x's which have mass and these y's which are massless. And then there are quartic terms. There are no cubic terms, but there are quartic terms. So these will provide vertices in AdS2 which will connect to bulk to boundary propagators and get the correlation functions. And again, expansion parameter is this string tension. So there'll be the string amplitudes will be powers in 1/² of lambda. So once we compute this correlation function, they will provide us with the interpretation will be in terms of these correlation functions for the fields on AdS side. So why this is also natural is essentially because of we can view string action. Classical three-level S matrix essentially comes from string action. So once you expand string action, you essentially get this correlation function. So quick comment that this AdS2 CFT duality which we get is kind of non-gravitational. There's no analog of stress tens, and AdS conformal symmetry here is exact, but there's no one-dimensional representation symmetry. So let me get to the results indeed. So in one dimension, there's only one cross ratio, so the correlation functions, they essentially have this structure. And in terms of this chi, cross ratio chi, we can consider OPE expansion in general. So these are F is conformal block in one dimension. So considering expansion in intermediate operators, one can actually, once we know 4-point function, we can extract anomalous dimensions of, we can extract dimensions of operators which appear in OPE. So this is a simple example how this looks like generalized free fields. It's basically the operators with no build of several free fields. Their correlation function is in terms of chi looks like this, and one can see what are the dimensions. You apply an OPE, one can see what are 3-point functions, etc. So 4-point function of S5 fluctuations, that's how it looks like. So there is a singlet part. So we have 4 scalars with 5 SO5 indices. So we can split into singlet part, antisymmetric part, traceless symmetric part. And these are functions of this cross ratio, which I'll just show how they look like. So essentially coming from disconnected part, which will be generalized free field part, and this connected part. And they are obtained basically as usual computation in AdS for Witten diagrams, but now in AdS2. So in terms of bulk to boundary propagators, 4 bulk to boundary propagators, etc. And what one gets is that's a key result. So one gets this function which appear in 4-point function as kind of ratios of this chi times logs. And the presence of logs indicates anomalous dimensions of the composite operators which appear in OPE, which can be extracted, and we can find them and see, for example, for this double product of 2 phi's, we indeed get this 2 pi, 2 minus 5 squared of lambda, which I mentioned earlier. But we also can extract 3-point function coefficients in this way. And generically, do I have 3 minutes more? 3, okay. Okay, so one interesting point that there is some universality in how these dimensions go with any n. N is number of derivatives. So this what appears in OPE when we took 2 points together, essentially bilinears of the fields times some number of derivatives along the line. And these go like this, and at large n. So that suggests there is some semi-classical explanation for this behavior. It's like analog of spin in one dimension would be, like analog of some kind of large spin expansion in one dimension. So we consider also mixed fluctuations. We can have some fluctuations in AdS5 and some in S5. There are similar results. And here the bilinears will be one scalar, one displacement operator. So here, again, there are similar expressions for the 4-point function, which we find. Again, they have logs and rational functions. Now, what I don't have much time to discuss is exactly the same story, but for standard Wilson loop. And here there is a big twist in the story, that now our scalars, there are 6 scalars, SO6 is unbroken, but we have Neumann boundary condition S5, which means that we need to average over S5. So we don't have a fixed point. So usually what we have is, if we have an ON sigma model, we if we just do naive perturbation theory, we expand near one point, we break SO6, say, to SO5 by parameterization, and we get, in general, this is bad because we'll get infrared divergence, etc. But in fact, if you look at composite operators, the operators which are SO6 invariant, they will still be fine. So in a sense, what happens in the case of Neumann boundary conditions, we have the operator which has 0 dimensions, like ordinary two-dimensional scalar, which will suggest infrared problems. But because of the corrections, it gets non-trivial anomalous dimension, and that starts with this 5 square root of lambda. And I'll just quickly sketch how this is done. So essentially, one needs to integrate over position on S5, and this can be viewed as doing everything in terms of embedding coordinates and expanding near some constant value on S5, but then integrating of this constant value. And doing this systematically, so zeta here are 6 fluctuations which are constrained to be orthogonal to this constant value, and then you integrate over this constant value. And this can be done systematically. All one needs to know essentially is a propagator on half plane, which is the usual kind of Neumann propagator on the half plane in this case. And doing perturbation theory, one compute 2-point function, finds this anomalous dimension, delta. There is a phi plus, etc. corrections. So the diagrams essentially look like this. So these are, instead of drawing this as a straight line, I draw it as a circle, the boundary. And these are propagators connecting the boundary. There'll be loops, there'll be fermionic loops, which we didn't compute so far. So we just considered mostly bosonic and tree level. And I'm ending with, so these are just examples of how this is done. Technically, this is non-trivial because the propagator is logarithmic. That's maybe one point which I need to make. So instead of usual Dirichlet bulk to boundary, now we're dealing with bulk to boundary, which is logarithmic, like this. And that leads to much more complicated integrals, which are not easy to do. And there are various tricks how to do that. But the end result of that is, so that's the key result which I want to show. It's 4-point function of four of these scalars, which will be 4 scalars in Young-Mills. So its expansion is square root of lambda, and given by all that kind of diagrams. And the leading correction, 1 over square root of lambda, it still contains logs. But the next correction, 1 over square root of lambda, which contain, for example, this diagram, which is main tree-level diagram, it is given by polylogs. So that's the first place where we see these polylogs actually in the tree level approximation. And question is how to relate to this one-dimensional bootstrap and how to interpolate to weak coupling. And one can extract anomalous dimension from that. So that's my final slide. So what I want to finish with is that we sort of have now understanding how to do these computations both in Dirichlet boundary conditions and Neumann boundary conditions. What remains open is how to do systematically loop correction with including fermions, and what is the intrinsic description of this induced CFT1. So one possible logic it's most likely it's non-local, and in fact there were some somewhat related models discussed as a possibility. But one could attempt to derive it systematically by starting at weak coupling, starting with fermionic representation for Wilson loop and integrate gauge field, and then see what one gets. It will be some kind of very non-local theory of one-dimensional fermions. There is a question about relation to integrability. It should be somehow encoded in this correlation function because strain action is integrable. But what is the precise connection? Maybe they should be somehow related to factorization of effective two-dimensional matrix in some way, but we don't have any light cone gauge here. Anyway, I stop here. Thank you much.